Hello, my name is LaWanda Hopefields, and I have the honor and the privilege of serving as the director for the Ronald E. McNair Post-Baccalaureate Achievement Program, also known as McNair Scholars. During this 2019-20 academic year, we are excited to celebrate our anniversary of 25 years on the Wichita State campus. Although during this year, we have encountered many challenges, as most of America has, we are so proud to still celebrate our students, and we have great appreciation for the faculty members who have stayed the course to bring this year's scholarly activities to a close. I would like to acknowledge my boss and mentor, Ms. Delta Q. Colvin, for her support during these most recent challenging times, but also for her confidence in me to lead this dynamic group of students. Miss Ashley Cervantes and Miss Nisha Green are the capable hands behind the scene, and a mere thank you is not enough for all that they do. They are the backbone of our program, and I am forever grateful. As we celebrate 25 years of academic excellence and 15 students who are completing their scholarly research, I also want to thank you as our supporters and as our listeners. Thank you for being there for the students and for the program as we celebrate 25 years of academic excellence. Enjoy these dynamic presentations.
My name is Joseph Sekavec. I'm a math major at Wichita State University, and my faculty advisor is Dr. Justin Ryan, and he's a part of the Wichita State University Department of Mathematics. Today we're giving a presentation over what we did. We modeled fluid flow past an object using Sage Math with the objective of eventually modeling fluid flow past an airplane wing. Here's an example of what it would look like past a tennis ball. Some mathematical background: we needed some complex analysis, some geometry, because there's some circles that we needed to turn into ellipses before modeling airflow over it. And we needed some known solutions from differential equations. So from complex analysis, we needed to know what analytic functions were. That is, that a function depends only on z, so d by dz bar must equal 0. And we also needed to know that the functions were harmonic, so the Laplacian must equal 0. And lastly, we need a Joukowsky map rather. And that's defined by w equals z plus alpha over z, where alpha is any real number. So to begin, we have horizontal flow. We let the imaginary part, which is the y-axis in complex analysis, equal a constant value. And then we plot streamlines over it. And then we introduced something called a power map, which means we raise z to the power of some number beta. On the left, we have a beta that is less than 1. On the right, we have a beta that is greater than 1. A good example of this in real life would be if something is flowing underneath an overhang or over a hill or a bridge. Now we do some uniform flow past an object. In order to do this, we actually need to know the stream function. We get this from differential equations. It is u times 1 minus 1 over r squared times r sine theta, where u is the velocity at infinity. So it's a constant value. Here we use 1 mainly for simplicity. And then we use that to plot streamlines across a circle, which is the cross-section of a cylinder. Here's some of the code that we use to plot this in Sage. Now we want to model fluid flow past an ellipse. We're going to apply this Joukowsky map that we talked about earlier, and that's going to squish the circle down to an elliptical domain so that we can more accurately approximate an airplane wing. Then we'll use the same function we used earlier, the stream function, to plot the streamlines over this ellipse. Here's some of the code that we used to go from the circle domain to the elliptical domain. Now we add something called circulation. And the circulation function is just defined by c times natural log of r. So as you change that C value, you're going to change something called stagnation points on your object. That's where the flow actually meets the object. And then you add it to the stream function, and it'll change things around. It'll change where those stagnation points meet, therefore it'll change how fluid flows past the object in general. Here's some examples of that. From left to right, we have one that we let C equal 1/2, then we let C equal 2, then C equal 2.2. As you can see, it drastically changes the stagnation points if you increase value of C above 1. We modeled airflow over an ellipse utilizing a Joukowsky map. We were attempting to model circulating flow over an ellipse with SAGE, but we discovered that some of the problems with the symbolic way we were doing things means in the future we'll have to use more numerical methods in order to plot this a little better. Thanks, I'll take questions now. Well, this is a simple model, but we can actually use it to do things like model airflow over an airplane wing if we actually apply more advanced differential equations later on if we continue. But this is the conformal map that you would use to do that. It's significant because engineers actually need some mathematical modeling whenever they're designing airplanes. Even though this is a simple model, it is the backbone of a lot of what people use later in more advanced models. It's very hard to actually plot some of this just using complex analysis, and it is actually something we ran into, and we figured out we're going to need to use numerical mappings and possibly use more MATLAB code. So that was some issues we ran into. It was actually kind of hard to model circulation over anything that wasn't a circle. This has been a presentation about research regarding fluid flow. Thank you all for coming.